Let me give you some examples of some very successful mathematical experiments from the early days of experimental mathematics with computers. I'm contrasting two examples because they are both very successful experiments, but as you'll see, one gives an output which is very directly usable. It's a counterexample for conjecture, whereas the other gives an output which is really much more vague in the sense that it really only leads to conjecture. These are sort of the extremes of what can happen when you engage in a mathematical experiment with a computer. The starting point of the first example is conjecture by Euler. Euler, by the way, is going to be one of the big heroes of this course. He was, of course, a very prolific mathematician, produced a lot of theorems and theories, but he was also an experimental mathematician, so of course not using computers, except perhaps he had a computer which was a person who would do computations for him. And many of these experiments resulted in conjectures that ended up being proved by either by Euler himself or by other people. The one I want to focus on is a conjecture which relates to sums of powers. Euler had the conjecture that if you have a sum of nth powers, let's say m of these terms, that add up to an nth power, then it's because there either is only one term to the left of the equation, so meaning that m is 1, or there is at least n terms, meaning that m is n or larger. What he was saying is that if you have a sum of nth powers and they add up nth powers, of course, of integers for this to make sense, and that these m nth powers add up to another nth power, y to the n, then n has to be bigger than m. The reason for conjecturing this was that Euler had actually proved that it was true for n equals 3. At least he proved that if you have two cubes and add them up, two cubes of integers, this can never itself be a cube, which of course is a special case of Fermat's last theorem, where you let m be fixed to 2 and let n vary. Based on this and perhaps some other experimental information, Euler made this conjecture. And this was one of the early triumphs of experimental mathematics on a computer, was this paper here, one of the shortest papers in math, I guess, in existence, which is essentially just a counterexample to Euler's conjecture. Lander and Parkin made an experiment on a computer. They simply looked for counterexamples to Euler's conjecture, and they were successful finding that these 4 fifth powers indeed add up to this fifth power. And that's it, right? So this is the experiment on one of these very old computers. This is like mid-60s. That the result of the experiment is simply a counterexample, which in its own right is a mathematical result that you can publish in a journal. Right? So this is really what is, I guess, the best that you could hope for when you're making a mathematical experiment, that you will actually directly from the experiment you can infer something which is new mathematical knowledge. But that is a fairly rare thing. Right, and of course it's even more rare that you refute a conjecture by Euler this way. So let me show you another example of an extremely successful experiment which has a very different kind of output. So the mathematics of this problem is a little bit more complicated, and I don't really want to give you all the details, but it relates to elliptic curves that are equations or subsets of the plane given by It's like a third order equation of this type. The two British mathematicians, Birch and Swinnerton-Dyer, so that's two people, Birch on one side and Swinnerton-Dyer on the other, started a computational investigation of such elliptic curves in the late 50s, and came up with what is now known as the Birch and Swinnerton-Dyer conjecture. So essentially, when you have an elliptic curve, there's a number associated to it, which is called the rank. It's a little bit difficult to explain precisely what that is. It has to do with a certain group that describes the rational points on the elliptic curve, that is solutions to this equation where y and x are rational numbers. So this rank is well known to be a very important property of an elliptic curve, but it's also well known to be quite difficult to compute. But what Birch and Swinnerton did was that they looked at some concrete elliptic curves like these ones here, where the rank was known, and then they made computations, and I will explain in a moment how it works, and saw simply by plotting things like this that there was a relation between the growth of the numbers that you can compute associated to these 5 different elliptic curves and the rank. So for these different elliptic curves, you have something which could be construed to be some sort of linear behavior. So you should note that there's a log axis down here, so it's not straightforwardly linear, but when you make such a plot, you get these 5 lines that seem to approximate the observations very well, and the slope of these 5 lines is directly related to the rank. So this is the content of the Birch and Swinnerton-Dyer conjecture. So more precisely, when you have an elliptic curve, you compute a certain number, the discriminant, and whenever you have a prime that does not divide this discriminant, it makes sense to look at the number of solutions to this elliptic curve mod p. Right? So you only work with the residues mod p, and then you simply count how many solutions there are where y and x are now no longer general real numbers, but they're just 0, 1, 2, 3, and so on, mod up to p minus 1, mod p. And of course you can have a computer compute how many of these solutions there are, and this is what they did. And they computed this number, pi e of x, which is some sort of joint information of how many solutions there are relative to p, and simply found that these numbers were growing at a rate which was given by a power law, so the logarithm of x to this power, where this power was exactly the rank. Right? So what we're seeing here is that the ranks are different, and this means that the rates of growth are different in a systematic way. Right? And the point is that this, to this day, is not something that we know. I mean, there's no hard evidence that this is true. In fact, let me show you. If you go to the Clay Math Institute homepage, they have these famous millennium problems, and if you click on it, okay, I'm going to have to take the Riemann hypothesis. That's not the one I want. Oh, here they are. So the Birch and Swinnerton-Dyer conjecture is simply on this list, and it's the only one of these famous mathematical problems that are based on computer experimentation. Right? So it turns out that the Birch and Swinnerton-Dyer conjecture, if you can prove it, you will explain a lot of things about how the rank behaves. You will have a tool to compute the rank, and it has all kinds of applications in number theory that are so important that it's now put on this list of extremely important mathematical problems. So, the point here is not so much to describe the Birch and Swinnerton-Dyer conjecture, but to emphasize that it's very likely that you can make an experiment that doesn't give you precise information like a counterexample or maybe a theorem, but it's still a very useful and successful mathematical experiment because it can show you that something might be true that then you can make into a conjecture and of course perhaps convince other mathematicians to study as indeed Burgin, Swinnerton, and I did. Right, so returning to this diagram here, what we're going to have to do is to learn how to make efficient experiments that will produce mathematical output, but we just need to be ready to accept that mathematical output is not necessarily a counterexample or a theorem. It could also simply be a phenomenon, a conjecture that is interesting to study.